Hey kiddos, this is a review for Spiral 5. We're going to start off with an optional section. If you're happy with your log grades, you don't need to do anything with this. And if you're not, you can use this as a chance to bring up your log grades. We're looking for exact values, so we're going to solve for our x value here. First thing we do is get this log by itself. And in looking here, we're going to do -4 to both sides. So I get 3 times the natural log of 5x minus 7 is equal to 7. I'm going to divide both sides by 3. To get the natural log of 5x minus 7 is equal to 7 over 3. To get rid of the natural log, I'm going to convert this to exponential form. So that's going to be e to the 7 over 3 is equal to 5x minus 7. I'm going to add 7 to both sides. We get e to the 7 over 3 plus 7 is equal to 5x. And then finally I'm going to divide both sides by 5. My final answer is going to be e to the 7/3 plus 7 divided by 5 is equal to x. For number 2, which I guess right below that, we can do the same thing, but instead of getting a log by itself, we've got to get an exponential part by itself. I'm going to -4 to both sides, and when I do that, we get 5e to the 2x minus 5 is equal to 3. Then we divide both sides by 5. And I got e to the 2x minus 5 is equal to 3/5. From this point, I'm going to convert this to log form. We're dealing with e, so we've got to use a natural log. The natural log of 3 over 5 is equal to 2x minus 5. To get the x by itself, I'm going to add 5 to both sides. The natural log of 3 over 5 plus 5 is equal to 2x. And then to finish this off, we're going to divide both sides by 2 to get the natural log of 3/5 plus 5 divided by 2 is equal to x. For problem 3, we've got to expand this completely, and I gave you a delightful problem that involves lots of crazy things. I can't really tell what's going on with those square roots in the denominator. It looks like one of those is supposed to be a cube root and one of those is a square root, maybe? But let's see what we can do. We know general rule of thumb that the top of these are going to be positive, and we're going to add those together. The bottom are going to be negative. So I'm going to break that up first by just kind of separating those out. So we get ln of a to the 5th plus ln b to the 7 plus ln c to the 8th minus ln w to the 11th minus ln square root x minus ln cube root y. The next thing to do is to bring these powers down front. Every single power comes down, and that includes our radicals. Square root of x is equal to x to the 1/2, and cube root of x is y to the 1/3. So that would leave you with 5 ln of a plus 7 ln of b plus 8 ln of c minus 11 ln of w minus 1/2 ln of x minus 1/3 ln of y. That would be fully expanded. For number 4, we're condensing. First thing I might do is to take a look at any coefficients, and I'm going to bring those up top. I've got a whole mess of them. So might we write this as log of 3 minus log of a to the 5th plus log of b to the 3rd minus, and 1/4 is a power, is the 4th root. So that's log of the 4th root of c plus log of d to the 3rd. Things that are positive are going to end up on top of my fraction. I'm going to have 1 log and then a nice big fraction on the inside. So you've got 3 b cubed and d cubed. And things that are negative, so a to the 5th and the 4th root of c are going to end up in my denominator. At this point, I am done condensing. For our second section, we're looking at limits, and we are trying to define what's going on with the limit as x approaches 2. For this thing to exist, the limit from the left and from the right must be equal. So let's take a look from the left first. From the left, I'm going to use the top stem, and the limit as x approaches 2 from the left of ln of x is going to be ln of 2. Okay, from the right side, we're going to have the limit as x approaches 2 from the right of x squared ln of 2. And when I plug that in, we get 4 ln of 2. Since these are not the same value, the limit is non-existent. For number 6, if a does not equal 0, in other words, that point doesn't just go away, then we've got to figure out what's going on with this limit. First thing I'm going to do, just to make sure, is plug this value in. So we get a squared minus a squared over a to the 4th minus a to the 4th, which is 0 over 0. And I know that that means I might be able to do some factoring. The top is going to factor into, I'm going to rewrite my limit. It's going to be x minus a and x plus a. The bottom is going to factor into x squared plus a squared and x squared minus a squared, which, hey, that looks familiar. This is what we just factored to get to the top stuff. So if we cancel those out altogether, we're left with 1 over x squared plus a squared. When you take that limit, you get 1 over a squared plus a squared is 2a squared, which happens to be answer choice B. For number 7, I decided to torture you guys a little bit. I know that these are your favorite limit problems, and I figured that I would talk about why some of these things are true. For the first part, we're looking at g of x. Okay, that's over here. And x approaches -2 from the left. So from the left side, -2, we're approaching a height of 1. X approaches -2 overall. So I've got to look at both sides, and cool, one's approaching 1 and one's approaching 4. Since we're approaching 2 different values there, this limit does not exist. For the next one down, since this limit does not exist, 5 times this limit also would not exist. Because even though we've got something different there, it doesn't affect the idea that we couldn't work from that anyway. Oh, that's fun. F plus g of x doesn't really work because there's no f. This is also fun because there's some great typos. Let's call this h plus g of x. That makes some more sense. So what we're going to have to do here is to take a look at the left and right again, but now we're going to add these together. I'm going to do this in purple if I can get my... Uh-oh, I don't know what I just did. Can you guys see that? I have no idea, so I'm going to undo that. Well, it's not letting me choose a different color right now, so that's okay. I'm going to erase the stuff that I did earlier so that we can see what's going on all together. Okay, back in action. So this is going to be h plus g of x, and we're going to take a look at the left and the right. So it's actually the same thing as this guy over here, so I'm going to ignore that. So h of x, as we approach the value from the left, so we're approaching a positive 4 and a positive 1. 4 plus 1 would be 5. From the right, so that's the limit as, scroll up a little bit, x approaches negative 2 from the right of h plus g of x. And from the right, we've got a limit of 4 and a limit of 1. So 4 plus 1 is going to be 5. Since both of these exist and they're equal to 5, that means the overall limit exists and is also equal to 5. We can do the same thing in looking at some other combinations. So if we're looking at g times h of x coming from the left side, so we're looking at the left side here is 1, and the left side here is 4. 1 times 4 would be 4. We already did this guy. F minus g, I'm assuming it's supposed to be h minus g. We'll do the same thing we did for adding, but subtracting instead. So the limit as x approaches 3 from the left of h, sorry, my handwriting is terrible today, h minus g of x. So we're approaching 3. It's going to have a height of 5 and a height of a half. 5 minus a half would be a 4 and a half. And then we're going to do the same thing from the right side. So that's the limit as x approaches 3 from the right. And when we do that, we get the same exact values. So h minus g. And from the right, we'd have, again, height of 5 minus a height of, don't know why I drew that on there, 0.5. Whew. My writing today is pretty extraordinary. And then we skipped one, so there's that, I guess. G of x minus 1, when you're trying to find the limit as x approaches negative 2, would be equivalent to saying the limit as x approaches negative 3 of g of x. One way to kind of eyeball this is just to look at, if I plug in negative 2 here, we've got g of negative 3. So that's really what we're looking for. Another way to think about this is that this is a translation of this entire graph to the right. So the point that used to be at negative 3 is now going to be at negative 2. And in either case, both of those have a height of 2 when you take the limit from both sides. Looking at number 8, we've got to deal with some continuity. In order to get credit for a question like this, you have to use limits. Otherwise, no credit can be earned. I want to be really clear about that. In order for this to be continuous at x equals 1, in other words, something's going on at x equals 1, that means I can't have that be true. K has to be some kind of value. So let's see what happens when x equals 1. Well, I'm going to start off with the limit from the left, because I know I'm going to have to deal with left and right at some point. That's going to be 2x squared minus 5x plus 3 over x minus 1. When I plug 1 in, I get 0 over 0. Okay, so something's going on here. In this case, there's going to be a hole in our graph. The top of this is going to factor into 2x and something, and x and something, because I'm going to multiply to a positive and add up to a negative. Both of those have got to be negative values. And in order for me to get to negative 5, we're going to have a negative 3 there and negative 1 there. My x minus 1's cancel out. That was another hint that was part of this problem. And what we're really dealing with is a reduced form of 2x minus 3. When I plug 1 into that, I get negative 1 as an answer. So from the left, we got to do the same thing. From the right. And you should rewrite this again, but I'm okay if you don't, because we get the same value if we plug in from both sides. That also means that f of 1 must equal negative 1. And if f of 1 is equal to k, that means k has to be negative 1. This is an example of the problem where you have to use that function value, not just the limits. Number 9, you're asked to find where some weird conditions are happening. Okay, so the limit exists. Same thing coming in from both sides, but f of k does not exist. So we've got to have some kind of hole in a graph. But a continuous-ish hole, where that's the only piece that's missing. It's a removable discontinuity. That looks like that's happening at x equals 4. So k would be, so that's a negative 4, not a 4. K equals negative 4. I've also got another one of those types of places when k equals 6. All right, looking at the second part of this, where the limit does not exist, but the value exists. So we're looking for some kind of a jump where we have one side that exists and one side that doesn't. And that looks like that happens at x equals negative 1. And that looks like that happens at x equals 2. And it looks like it happens at x equals 8 as well. So we got 3 of those ones. And finally, we're into some derivative stuff. I'm so excited. First thing first, you got to determine the slope of the secant line on this interval. Well, a secant line is a line that connects two places on some kind of a curve. So we've got to do first is find what those 2 points are. I'm going to use these as my two x values. That's x1 and x2. Means I got to find some y values. If I plug negative 3 in, we get f of negative 3. And that's going to be negative 3 squared plus 3 times negative 3 minus 1, which is negative 1. So that gives me the point, negative 3 comma negative 1. We're also looking at f of 1, which is going to be 1 squared plus 3 times 1 minus 1. 4 minus 1 is going to be 3. So 1 comma 3. Finding the slope between those 2 points. 3 minus negative 1 is going to be 4. And then I have 1 minus negative 3, which also is 4. We have a slope of 1. Determine the slope at x equals 2 using the definition of derivative. That's the limit as x approaches h thing. Sorry, limit as h approaches 0 thing. So in looking at that, first thing I might do is to find f of x plus h, just so I can use this. I'm going to definitely have to use some more space for this. It's going to be a long problem in marker. And for the x squared part, that would be x squared plus 2xh plus h squared. For the 3x part, that would be 3x plus 3h. And then for the number, it just goes in on its own. Okay, so from that, I've got to subtract the original function. So I'm going to begin building this limit now. So this is the limit as h approaches 0. You need that in order to use the definition derivative. And this is going to be x squared plus 2xh, and yes, I am literally just copying this line down, plus h squared plus 3x plus 3h minus 1. And then minus the original function. So the original function was x squared plus 3x minus 1. And all of this is going to be divided by h. Really, that's going to be x plus h minus x. It's a slope. But since we have that simplified to h, we often just leave that out. My x squareds reduce. My 3x's reduce to 0. Minus 1 minus 1 also goes to 0. And you're left with a new expression. The limit as h approaches 0 of 2xh plus h squared plus 3h all over h. I've seen a number of you do this different ways. One option would be to factor out an h, and that's totally fine. And you get 2x plus h plus 3 over h. Those reduce, and you're left with 2x plus h plus 3. When you plug h equals 0 in, you get 2x plus 3. So if we have something that is f of x, f prime of x is going to be 2x plus 3. The last piece of this, it asks us to find when x equals 2. What that means is we have to plug in 2 to our derivative, and we get 2 times 2 plus 3, which is 7. For the third part, we've got to write an equation for the tangent line when x equals 2. I need a slope, and I need a point. The slope is going to come from my derivative. Derivatives are slopes of tangent lines. So when we did that, we actually found the first part of this equation. The second part is I need a point. And to do that, I need to find f of 2. So it's going to be 2 squared plus 3 times 2 minus 1. 10 minus 1 is going to be 9. My point would be 2 comma 9. The equation for this tangent line would be y is equal to 9 plus 7 x minus 2. For number 11, we have to use the product rule. I'm going to leave the derivative rules up on the board for this spiral and for the next spiral, and these are feedback sections. After that, they're going to go away. And I've got to identify that this is f times g, where x is f and sine of x is g. For the product rule, we're looking for the second times the derivative of the first, plus the first times the derivative of the second. So just kind of writing this out, that would be sine x, and the derivative of x would be 1 times, let's see, plus, the first is going to be x, and the derivative of sine of x is cosine of x. So we've got sine x plus x cosine of x. Nope, yep, nope, nope, nope. And you're done. For number 12, we've got to take the derivative of something that looks like a polynomial, so I can just power rule everything. That's going to become 15x to the fourth minus 6x squared plus 3, and then plus 0. I don't need to write that. For the second one, we've got to do the derivative of sine and cosine here. The derivative of cosine is negative sine times 3 would just be negative 3 sine of x. The derivative of sine is going to be cosine, so it would be plus 2 cosine of x. For C, we've got to use the quotient rule. We've got a bottom and a top here. I'm going to do the bottom first, so that's going to be x squared plus 2x, all squared. And then the top of this is going to be the bottom times the derivative of the top. So x squared plus 2x. The derivative of the top is going to be negative cosine x minus the top times the derivative of the bottom, so sine of x, multiplied by 2x plus 2. Totally okay if you leave it like this. Not much else you can do with that. For number D, we've got two things being multiplied. This is going to be a product rule. So we got second times the derivative of the first, cosine of x multiplied by 6x. And then to that, we're going to add the first, 3x squared, times the derivative of the second, negative sine x. And at that point, you're done with that as well. Not much else you can do.